Hello everyone. In this video we will be doing a timing analysis with ideal clocks but with multiple clocks. So things change a bit over here and we will be trying to explain how does the things change and what all things that we need to consider while doing a timing analysis or while doing a setup timing analysis between multiple clocks. So the first change, it's pretty simple. So the first change is we have, let's say, two clocks. The first clock has got a period of 1 nanosecond, and let's say we had defined two clock ports. One was clock 1 and the other was clock 2. So let's call T1 as 1 nanosecond. So T1 injects a clock with a period of 1 nanosecond. Okay, and clock 2 is, let's say, 1.5 nanosecond. The period of clock 2 is 1.5 nanoseconds, which just says that the clock 2, a PLL which is sitting outside the chip is supplying a clock of period 1.5 nanosecond through the clock port clock 2. Okay, so we have clock 1 as 1 nanosecond, clock 2 as 1.5 nanosecond, and also we have some related timing paths, and these two clocks are related. When I say these two clocks are related, it means that there is a valid timing path between them, and the valid timing path is this one, the launch flop and the capture flop over here. And we will be very soon showing in our design where we have this kind of scenario. We have already seen this. We'll try to revise that a bit. So we have a scenario in our design where we have a launch flop clocked by a clock 1, and we have a capture flop which is clocked by clock 2. Okay, so this scenario does exist on a design, and these are related clocks, and when I say related clocks, there is a valid timing path between clock 1 and clock 2. Okay, so the combinational delay remains the same. It's called as theta. So let's draw the clock 1 over here. The clock 1, we have the clock 1 period is 0 to 1 nanosecond. Okay, and the clock 2 period is 0 to 1.5 nanosecond. Okay, let's bring it on the top of each other and try to analyze this part. So the analysis pretty much remains the same. Only at what point do we need to analyze this thing, that has to be found out. So here are a few steps or few tips to do it. So the first step is to expand the clocks. So we have to expand this particular clock till a point where you see a common edge. Okay, so because the concept is the setup timing analysis works on rise to rise edge, the rise edge at the launch flop and the rise edge at the capture flop. It works on that concept. So you need to find a common rising edge, the next common rising edge. In case where if there was single clock going across the flops, we didn't have that problem because the next rising edge was common to both of them. Okay, so in this case what we have to do is, the first thing, we have to expand the clocks in such a fashion that we arrive at some point where we find a common rising edge. That is the first step, and very soon we will be determining, we will be identifying the reason why we need to do that. So first let's try to expand it. So we'll expand this from 0 to 1 to 1 to 2, and we'll expand 0 to 1.5 and 1.5 to 3. So still we don't have any common rising edge. Let's try to expand it even more. So we expand this one to 0 to 2 to 3, and we expand this 3 to 4.5. But what you see at this point 3, at this point 3 nanosecond, you have found the next common rising edge. Okay, so this is where you find the next common rising edge, and that is the first step to do. So whenever you try to do a timing analysis with multiple clocks, you will see some messages or in your log saying that expanding clock X, expanding clock Y. So this is what it does. It expands till the point where you see a common rising edge. Okay, with that said, now let's try to look into the analysis. So in the analysis part, what we have to do is we have to find out the shortest timing window or the shortest window available between the launch clock edge and the capture clock edge. What does that mean? So for example, you launch at, let's say, clock 1, you launch at 0. Okay, so the next rising edge that arrives at clock 2 is this one, and the time period between this clock edge, which is at the launch, and this clock edge, which is at the capture, the time required for the data to get captured is 1.5 nanosecond. So the window is 1.5 nanosecond. Okay, but this might not be always true. And why is that so? Let's look into another scenario. Let's say now the data comes at this particular edge, comes at this particular rising edge, the launch flop or the data is being sent at the rising edge of clock 1 launch edge, which is this one. Okay, and data gets captured the second the next launch the next rising edge that the circuit sees at clock 2 is this one. Okay, so data gets getting captured at clock 2. In this case, the window that you see is 0.5 nanosecond only, and this is in contrast to the previous one where we saw it was 1.5 nanosecond. So had we had done the analysis at 1.5 nanosecond, and if there was a case which was something like this where the data is expected to reach within zero point 0.5 nanosecond, we would have almost violated the circuit, almost violated the timing. Okay, let's look into some other combinations of window. Let's say we go into the third edge, which is this one. So data launches, or the clock one, the launch flop launches the data at this rising edge of the flop. Okay, of this rising edge of the clock, and the next rising edge that you see from this point over here onwards to clock 2 is this one. So this is the next rising edge, so capture will happen at this point. And now if you see the window, that is even less, it's 1 nanosecond. So we started with 1.5 nanosecond window, which was this and this. Next we started with 0.5 nanosecond window, which is this and this, and the final one which we found out was 1 nanosecond window, which is between this and this. So there are three scenarios. Let's say if you try to close your design, or you try to optimize your data path in such a fashion that the combinational delay theta is, let's say, is less than 1 nanosecond, or let's say it's 0.9 nanosecond. Okay, so if the data was, if the combinational delay was optimized to achieve 0.9 nanosecond, that will satisfy a condition which is this one, when the data is launched at 2 and captured at 3. But in a case where the data will be launched at this point and captured at this point, and this is a valid scenario, if you practically see this scenario, and this scenario is valid, so the data can be launched at this edge, and it finds a next immediate edge, which is this one, and data can be captured at this edge. Okay, so the shortest window that you see, which is of 0.5 nanosecond, this scenario is a valid scenario on your circuit, and your data can be getting launched and captured within this period. In this case, when you have your data path delay which was optimized for 0.9 nanosecond, it will violate this scenario by 0.4 nanosecond. So the window that is available for us is 0.5 nanosecond, but your data path delay is 0.9 nanosecond, and this scenario might get violated. So we have to take care of this kind of scenario as well. So while we do things with multiple clocks, we have to take the worst case possible. So it's always called as the worst case scenario, that the circuit might pass in this scenario where you launch your data with this rising edge and capture your data with this rising edge. The circuit will also pass with a scenario where you launch your data with this rising edge and capture your data with this rising edge. But whenever the circuit hits this kind of corner case, it will fail, and the results will be unpredictable. So it's always better to analyze your circuit at the worst possible condition. In this case, the worst possible condition is 0.5 nanosecond, and this is where you actually design your circuit to be, or try to optimize the combinational delay to get a delay which is less than 0.5 nanosecond, and then finally you have your interclock uncertainty and so on. So the condition becomes is your theta should be less than your setup shortest window, which is 0.5 nanosecond, minus setup uncertainty, which is like 10 picosecond, and minus setup time, which is 10 picosecond, minus interclock uncertainty. So there are two set of uncertainties that we define. One is the same clock uncertainty, and one is the interclock uncertainty. So interclock uncertainty is been kept as 0.1 nanosecond. So what we'll do is, since I'm running a bit late out of time, we have to discuss this particular equation in a bit more detail. So let's try to take this particular equation along with this particular circuit, and then we will try to get the real value of the conventional delay through the design that we have been working on. So let's try to do all this in the next video. Thank you.